So now we're going to look at partial sums of geometric sequences. So if we're going to add up the terms of a geometric sequence and add a finite number of those terms up, then we can look at what we call the nth partial sum. So here's the notation for that. So the nth partial sum, we subscript this, or put the index here, k equals 1 to n. And then the first term is a sub 1, the second term a sub 1r, etc. This would be a sub n. The last term is a sub n. So this would have n terms. Right. So the nth partial sum means there's n terms in the sum. So we're going to derive the formula for the nth partial sum now. So let's start with s sub n. We know that it's equal to the sum of the first n terms of the sequence. So a sub 1 plus a sub 1r plus a sub 1r squared, etc. And then this next step isn't obvious, but what we want to do now to derive this formula is to take both sides of this equation times r. So r times s sub n is equal to a sub 1r plus a sub 1r squared plus a sub 1r cubed, and etc. And then this last term, when you take it times r, will be a sub 1 r to the n. So the term before it will be a sub 1 r to the n minus 1. And I'm going to write that down because what I want you to see next is that if we subtract these expressions, so s minus r, s sub n, sorry, s sub n minus r, s sub n, if we subtract these expressions here, you'd have to subtract every term. So what's going to happen is this will cancel this will cancel this, etc. The next term here cancels this, and then notice these also cancel, and so everything basically collapses except for this first term and this last term. So you end up with a sub 1 minus a sub 1 r to the nth power. And now we can get our formula for s sub n by factoring s sub n out. And, well, I was going to wait to do this till the end, but I guess I'll do it now. We can also factor a sub 1 out here. So we get 1 minus r to the n. And then that implies that s sub n equals a sub 1 times 1 minus r to the n over 1 minus r. So there is a formula for the nth partial sum where we don't actually have to add up all the terms. We just need to know the first term, and we need to know the common ratio. And of course, this n is the, how many terms we want to add up. So of course, that's the formula we just derived. So now let's go ahead and use it. Find the sum of the first 20 terms of this geometric sequence. So a sub 1 is 1, and it's pretty easy to see that r is 0.7. And we want the first 20 terms, so we want to find s sub 20, n equals 20. So s sub 20 will equal a sub 1 is 1 times 1 minus 0.7 to the 20th over 1 minus 0.7. So this is not going to be a very nice number because you've got 0.7 to the 20th. I would just simplify if you had this for your answer, I'd be fine with that. But let's go ahead and put it in our calculator, see what we get. So that's the numerator, and then divided by 0.3. So that's 3.33067, etc. So the ellipses just mean this, of course, keeps going, just so I don't have to write all those decimals down. And you know, as long as you had that on the test, I'd be happy with your answer, to be honest. Okay, so let's go on to the next problem. Okay, so in this problem we have, well, actually these three problems are all related. We have three different sums that we want to find. And notice that each of these summations, you've got a 5 and then times 3 to a power. So these are all geometric in form. R is going to be 3 in all of these. But the thing that can get a little tricky with the indexes here is what is the first term of the sequence isn't necessarily the 5. It depends on how this is indexed. And likewise, there's not necessarily 10 terms in the sum because you have to look at where k starts. This first one does have 10 terms because k goes from 1 to 10. But this one actually has 11 because k goes from 0 to 10. So you have to start with 0, so that's an extra term. So you have to be a little bit careful about just saying, oh, well, I'm looking at for s sub 10, a sub 1 is 5, and r is 3. That's not necessarily true. You have to consider what's happening with the index as well. So it's pretty easy to see there's going to be 10 terms here, right? And when k is 1, the first term is 5, right? This is 5 plus 5 times 3 plus 5 times 3 squared, etc., plus 5 times 3 to the 9th. So that is 10 terms. We already had mentioned that, or at least I did, right? But look at what happens in actually this one. When k is still 1 to 10, there's still 10 terms, but because this starts with k instead of k minus 1, you get 5 times 3 is the first term, plus 5 times 3 squared, etc., until you get up to 5 times 3 to the 10th. So there are 10 terms, but the first one is 15. Whoops, let me do this. I'll just do this, 10 terms. But this is 15. So a sub 1 isn't 5 in this problem. A sub 1 is 15. And in this one, a sub 1 is 5. So they look very similar, but there's a slight difference. You have to pay attention to the index and the power, you know, how this is denoted here, or I should say what the formula is, because that can affect what the first term is. And this one clearly has 11 terms because you're starting at 0 instead of 1. So here we'd have 5 plus 5 times 3. It starts out just like this one, but then it goes up to 5 times 3 to the 10th. So here's 10 terms, and this is an 11th. So this one actually has 11 terms. So you have to be careful and think about those things a little bit. So this one we're finding s sub 10. And all of these clear, r is 3, right? I didn't write that down, but r is 3. So s sub 10 is a sub 1 is 5 times 1 minus 3 to the 10th over 1 minus 3 for this problem. So again, you can pretty much leave it like that, but you should simplify the denominator. I would ask that you do that and put a negative 2 there. But let's actually, for this one, let's get the answers. Just because they're similar, I want to be able to compare the numbers. So let's see, 5 times 1 minus 3 to the 10th, and then divided by negative 2. So this one is 147,620. And then in this one, we're actually finding S sub 11 because there's 11 terms. We still start with A sub 1 as 5. And R is still 3. So 5 times 1 minus 3 to the 11th over 1 minus 3. So this time, and we can see the difference between these would just be this last term. You're adding this extra term. So what I want to do is just like compare and think about that. So 5 times 1 minus 3 to the 11th by negative 2, 442,865. So notice if I took 147,620, move that over, plus 5 times 3 to the 10th and I get that answer. Okay, so these formulas, or this formula works, obviously. All right, and the last one, A sub 1 is 15 and R is again 3. So S sub 10 is 15 times 1 minus 3 to the 10th over, again, negative 2, 1 minus 3. And if you compare this one to this one, wait, no, sorry. This one, I'm sorry. Notice this part here, these 10 terms are these 10 terms. So at this one, the answer should be 5 less than this. This is the only extra term. So I should get 442,860 for this answer. And we'll just verify that. Divided by negative 2. And that's exactly what we get. Okay, so if the numbers, again, if they get really big, it's okay to leave it like this. But if they're not too bad, I can go ahead and calculate. Okay, so the reason for these 3 examples is to show that you kind of need to think about, what is A sub 1 and how many terms there are in the sum. So check those things. So check for A sub 1. It's not always just what you see here. And I didn't need a comma there. The number of terms in the sum. Alright, what do we got left here? I think I'll take a break here. Oh, excuse me, I'm tired. And we'll pick up here in the next video.